Let's go ahead and start our lecture on chemical kinetics. So far what we've done in this class is we've looked at what happens in a chemical reaction. So here let's take a look at this generic reaction. Here the capital letters represent the reactants and the products, and then the lowercase letters represent the coefficients. So it's telling us that A plus B goes on to form D plus E, and then the coefficients tell us in what ratio this reaction is occurring. So the questions that we're going to be asking ourselves next are, what extent does this reaction happen to? And we're going to answer this question later. But right now we're going to focus on how fast and by what mechanism does this reaction occur. So whenever we're looking at the rate of a reaction, we're looking at the kinetics of it. So the speed or the rate at which a chemical reaction occurs. So we're no longer looking at static systems. We have A plus B, and then it's C plus D. So we have reactants going to products. Now we're looking at how fast this change is occurring. And we're going to start to measure a reaction rate. And this reaction rate is going to relate the change in the concentration of the reactant or the product, whatever you're interested in, with respect to some amount of time. So we look at this schematic down here at the bottom. This first box represents time 0, and then the second box represents time 1, and then time 2. So we can't really look at a reaction at the molecular level with our eyes, and we can say, okay, well, we started with 4 molecules of A, and then we're going on to form some amount of B. But you can see here that you can start to take into account how fast this change is occurring. So we have 4 molecules of A going on to form 2 molecules of A that haven't reacted plus 2 molecules of B that have formed. So 2 molecules of A have decomposed. Okay? And then going on all the way over to time 2, another molecule of A has decomposed and another molecule of B has been formed. Okay, so we can't really look at this at the molecular level. So we're going to have to start to think about, well, how can we make these measurements in the lab? Okay, so as we're thinking about that, the last thing that we need to introduce is this idea of a rate constant. And this is just a proportionality term that relates the reaction rate to the concentration of the reactant. And we'll talk about that more later. Okay, so how can we measure the rate of a reaction? Well, we know a reaction's occurring if we have a color change or if gas is being generated. So it would reason that we could use either UV-Vis spectrometer to look at the change in the absorbance of a particular wavelength of color, or measure the change in pressure of a gas. So we can start to think about measuring these things like we did in Beer's Law Lab or with the gas laws lab. We can start to measure the rate. How fast is the gas being generated? How fast is the color changing? How much is the absorbance changing by? So these reaction rates are given as a change in concentration over the change in time. Just to review, the delta sign represents the change, and then anything in brackets, that represents the concentration. So for products, we'll see an increase in their concentration over time, and for reactants, we'll see a decrease in the concentration over time. And since we have a change in concentration, so we'd have a difference in the molarities over a difference in the times, we're going to end up with units of molarity per second. Okay, sometimes you might see this in terms of molarity per minute or hour or millimolarity, something like that. It just kind of depends on what the situation calls for as to what units you use. But we do use molarity instead of moles because we want the rate to be independent of the scale. So we want to be able to determine the rate whether we had 200 milliliters of a sample or we had 5,000 milliliters of a sample if they were both at the same concentration. We don't want to have to go through and calculate the moles, so we just want to use the concentration. As we look at this particular reaction, the dinitrogen pentoxide reacting to form nitrogen dioxide and oxygen, we're given a data table, and now we're able to start to compare some of the concentrations that are given in molarity. But we can see that the dinitrogen pentoxide concentration decreases with respect to time, whereas the concentration of nitrogen dioxide and oxygen is going to increase with respect to time. Okay, so this is going to, again, reactants are decreasing over time, products are increasing. So we can find the rate of formation or the rate of decomposition, and there's a couple of different ways that you can do this. Here we're just going to pick the time step from 300 to 400 seconds, but nothing says that you couldn't choose 0 to 700 and find the average rate of formation. And we'll talk a little bit more about the different rates that you can measure whenever we analyze this problem graphically in just a minute. So as we look at the rate of formation of oxygen, we take the concentration of oxygen at time 2 minus the concentration of oxygen at time 1, which again we chose 400 and 300 seconds. So we're going to use these data points right here. So we find the difference, divide by the change in time, which was 100 seconds, and we find the rate of formation to be 9 times 10 to the negative 6 molarity per second. Well, how are you going to find the rate of decomposition or formation for nitrogen dioxide or dinitrogen pentoxide? Well, for the formation of dinitrogen or nitrogen dioxide, let's go ahead and just use the exact same time step. So we'll use that 0.0197 molarity minus 0.0160 molarity, all divided by the time step. Upon plugging that in, you should find the rate of formation for NO2. And one of the ways that we'll write this is like this. We'll say the change in concentration of NO2 over the change in time equals 3.7 times 10 to the negative 5th molarity per second. Okay, so let's think about the decomposition of dinitrogen pentoxide. So as we look at this, notice that the concentration is decreasing. Okay, so if it's decreasing, that means our rate is going to be negative. So if we plug this in, should look something like this. We should end up getting a rate of negative 1.9 times 10 to the negative 5th molarity per second. Well, do you need the negative sign or not? Well, it depends how the question is written. If it says, what's the rate of N2O5, it's going to be negative. If you say the rate of decomposition of N2O5, decomposition implies that negative sign. Just like exothermic implies that there's heat released. So if we said how much heat was released, you'd say 100 kilojoules. You probably wouldn't say negative 100 kilojoules. So it depends if you have decomposition or something like that written in there. All right, so let's look at this problem graphically. Okay, so here you can see that we're just looking at the change in concentration over the change in time. So we're looking at this tangent line. So we're kind of finding the derivative right there over a certain amount of certain time step. So there's a couple of different rates that we can have. Okay, let's see if we can find them. We have an average rate, an instantaneous rate, and an initial rate. So let's talk about the difference of these rates. So an average rate, we tend to think about it being the average over the whole time sample. So the change in concentration from time equals 0 to time equals whatever the reaction was stopped being measured. Okay, so that would be an average rate. Really, all of these are average rates, even all these time steps from 300 to 400 seconds. Whenever we think about an instantaneous rate, we start to change the time step so it's really, really small. Okay? So what we'll see is that if you're looking at an instantaneous rate, okay, time step is really, really small. And whenever we say an initial rate, we're looking at an instantaneous rate at time equals 0. So we're looking at a really, really, really small time step at the initial concentration, okay, at time equals 0. But you can relate this to driving a car. If you were driving from here to St. Louis, okay, so let's say that this represents here, this represents St. Louis, and the line is the distance traveled over time. Okay, so the change in distance over the change in time. So if you were looking at your average speed on the trip, you would take final distance, so the total distance traveled, divided by the change in time. If you're looking at instantaneous speed, or how fast you were going, maybe whenever you got pulled over, they're just looking at a really small sample. Okay? So let's go on to talk about these, how we can write a rate expression for this general rate of reaction. So if we had 2 moles of dinitrogen pentoxide going on to form 4 moles of NO2 and 1 mole of O2, okay, we could say that 2 moles of dinitrogen pentoxide disappear for every 4 moles of nitrogen dioxide that's formed, and 2 moles of dinitrogen pentoxide disappears for every 1 mole of oxygen that's formed. So how can we compare these rates? Okay, so we're going to have the change in concentration of N2O5 over the change in time. Well, here, what we'll see is we can set these rates equal to each other, but then we need to take into account the number of moles, how fast this is going. So if there's 2 moles that are disappearing, we're going to put a negative sign here to represent that it's disappearing. Then we're going to put 1 over 2. Okay? But then over here for the formation of NO2, there's 4 moles of NO2 that are being formed for every 2 moles of N2O5 that are decomposing, so we'll put 1 over 4. Okay? And then if you were to go through and multiply this both sides by 4, if you wanted to find the rate of just NO2, what you'd find is that it's going to be twice as fast whenever you multiply both sides by 4. It's going to be twice as fast as this rate here, the rate of N2O5. But let's go ahead and finish writing out our rate expression really quick. So we can also set this equal to the rate of formation of oxygen, which is the change in the concentration of oxygen over the change in time. So this is our general rate expression. And you can even write this rate expression for this general reaction here. So reactants, since they're disappearing, we always have a negative sign. It's 1 over the coefficient times the change in concentration over the change in time. Okay, since it's a reactant, it's negative. If it's a product, then it's positive. So we'd have 1 over d, little d, times change in concentration of D over change in time equals 1 over little e times the change in concentration of E over the change in time. So this is your general rate expression. So if you see something asking for the rate expression, this is what you're going to do. Let's go ahead and look at another example of this. So here, the first thing we need to do is write a balanced chemical reaction, okay, because we're asked to write a rate expression. So go through and balance it. Well, your nitrogens are balanced, that's good, but then you have 3 hydrogens in the reactants, only 2 in the products. So whenever you go through and balance that, you should have a 2, a 3, and a 2 here to balance the nitrogens. Then you have to balance the oxygens. Well, you have 2 oxygens in the reactants, 5 in the products, so you can either put 5 halves here, or you can go through and double everything. It won't matter because it will all cancel out whenever you do the math. So you could have 4, 5, 4, 6. Let's go ahead and write the rate expression for this. So NH3, as reactants will have negative 1/2 times the change in concentration of NH3 over the change in time. And this will be equal to negative 2/5 because it's 1 over the coefficient. So it'd be change in concentration of O2 over change in time. Now the product's 1 over 2 times change in concentration of NO over delta T, which is equal to 1/3 times the change in concentration of water over the change in time. So this is your general rate expression. So you should be able to write this for any chemical reaction. The next one that we're going to look at, we're actually given the rate of formation. Okay, so here we have this bromide ion plus bromate ion plus the hydrogen ion yields bromine plus water. Hopefully the reaction's already balanced for us. So then, as we look at this, whenever it says the rate of formation of bromine is this, what this actually tells us is that anywhere that we have delta Br2, so bromine over delta T, we can substitute in 6.0 times 10 to the negative 6 molarity per second. So you can start out by writing the general rate expression for all of this. In the interest of time, I'm just going to compare it to the individual pieces. So here, for the first step, calculate the rate of decomposition of BrO3 minus. Well, we'll go ahead and write out just this part of the general rate expression. So we have the bromate ion, the change in time, is equal to 1/3 times the change in bromine concentration over the change in time. All right, so what we can do is we can substitute in this right here. And what this will tell us is that the rate of decomposition of the bromate ion is 1/3 that compared to bromine. So the formation of bromine is 3 times faster than the decomposition of this. So if we plug this in, we should end up getting our rate of decomposition is 2.0 times 10 to the negative 6th molarity per second. If we're looking at the rate of formation of water, we can write out this part of the expression, setting the two equal. We have 1/3 change in concentration of bromine, change in time, is equal to 1/3 change in concentration of water over change in time. Okay, well here, this factor of 1/3 is going to cancel out. So the formation of water, that rate of formation of water should be equal to the rate of formation of bromine. So go ahead, why don't you try on your own to compare the rate of formation of bromine to the rate of composition of the bromine ion and then the hydrogen ion. And then we can compare those answers later. So next time we'll pick up with rate laws and reaction orders, but go ahead and keep working on those general rate expressions.